back, Energy 301 students. It's Dr. Shragi, and we're just going to, almost to the end here of the first module of the course that's just sort of an overview of the terminology that we use in physical meteorology so that we have some terms that we can use when we're talking about the factors that are necessary to statistically model electrical load and yield. And the one we're on right now is humidity. Now, humidity is a really tricky concept in atmospheric sciences. Atmospheric science majors often have a number of courses that have a lot of the content about explaining the amount of water vapor in the air. And if I just wanted to just use a real simple, loosey-goosey kind of term here to describe humidity, I'm just going to say that when we use the word humidity, we're just talking about how much water vapor is in the air. As it happens, water vapor in the air is a relatively difficult concept to quantify, and it can be really tricky to measure. It varies a great deal from time to time, and from place to place, and from from one height to another in the atmosphere. Quantifying moisture in the atmosphere is actually a surprisingly difficult problem. From the point of view of the energy course here, the good news is it doesn't have a lot. Humidity doesn't have a lot of direct impact on the production of energy. It can have some effect on yield because, like, for example, air conditioners get a great deal less efficient as it gets very humid. But this problem of the water vapor concentration being extremely variable does add a real wrinkle in meteorology. I mean, just to kind of give you a sense of the flavor of the problem, here's just a kind of corny map of average relative humidity in America. I believe the caption says in July at noon. And, you know, you're probably not hugely shocked to discover that the relative humidity is low over places like Nevada and is high over places like Florida. And sure, that fits our intuition, but it's not at all clear looking at this image how things would change at different times of the year or at different times a day. This is meteorologically a difficult chart to be making any sense of. In the same sort of way, here's a water vapor satellite image. You're probably pretty familiar with, like, the kinds of satellite pictures where, you know, the satellite imager is just taking literally a picture of what it sees below. But actually satellites can do a lot of different things, and one of the things they can do is produce estimates of the amount of water vapor at different heights in the atmosphere. This happens to be estimates about, I don't know, 4 or 5 kilometers above the surface, something like that. And you can see as this animation is playing out that there's a lot of variability here. There's any given location, the amount of water vapor is changing rapidly from one moment to the next. There are patterns. There's places that are humid. There are places that are dry. It's a very complicated quantity to get a handle on. So when we're talking about humidity, we're going to have some way to actually, you know, quantify it and measure it and so on. And it turns out there's several different ways to do this, and all of them are going to require some sense of what we mean when we describe air as being saturated. Saturated is an important vocabulary word in atmospheric sciences. And before we talk about that, you know, the word saturated kind of loaded with, you know, images. You probably could picture like a sponge that is saturated with water. That's both a good and a bad image to have in your head. I mean, on the one hand, it is saturated, the sponge is saturated in the sense that, like, there no more water can fit in it. Okay, I like that aspect of the word saturated. Well, it's not going to hold any more water. Okay, I like that better. All the space is full of water. Well, I'm not going to like that so much. You know, when air is saturated, it doesn't mean like there's no room for any water vapor molecules, but it does mean that it's holding all the water vapor molecules it can. And to get to the bottom of why that would be, we're going to do a little thought experiment. Before we start the little thought experiment, though, I want to clarify something about what's going to happen here. We're going to have this jar with water and air in it, and we're going to keep track of how much evaporation is happening as water from the liquid evaporates and becomes a vapor up there in the air, and how much condensation is happening, how much water vapor in the air is turning back into a liquid and joining the liquid at the bottom half of the jar. Both processes are happening all the time. At any given moment, any given liquid water molecule has a finite chance that it's time, it's going to evaporate and join the vapor. Same with any given moment, any given water vapor molecule has a certain finite chance that it is going to condense and return as a liquid back down to the bottom half of the jar. Both processes are happening all the time. The question is which one's happening faster. If the evaporation rate is greater than the condensation rate, we are taking liquid water away and putting it up in terms of water vapor in the top half of the jar. If the condensation rate is greater than the evaporation rate, we are taking water vapor out of the air and returning it to the liquid overall. And if the two are the same, if the evaporation rate and the condensation rate are the same, then we're kind of stuck. The amount of water vapor that's in the air is not going to change. So we're going to use these ideas of condensation and evaporation in this little thought experiment. So we start with a jar, we've got water on the bottom, and we're going to start with dry air on the top. No water vapor at all. We can ask what's going to happen here. Well, we can start off and say, well, we can't really have any condensation right now because there's no water vapor molecules in that dry air at the top. So we don't have any condensation going on, but we have lots of liquid water molecules down there at the bottom. So some of them will evaporate. It's just their time. There's a finite chance any given liquid water molecule will evaporate during this 1 second. It's a small chance, but any given one, there's zillions of them there, it adds up to some evaporation. So at the beginning of our little experiment here, the evaporation rate is bigger than the condensation rate. The condensation rate right now is 0. So we are transporting water from the jar, from the liquid, up into the dry air, which really isn't all that dry anymore. We probably should call it moist air. Wish we had a way to quantify that. We're going to use the notion of vapor pressure as a way to quantify that. If you've had a class like physical chemistry or something like that, you might have heard the term partial pressure. It's the same idea. Meteorologists call it vapor pressure. But it's just to measure the pressure of the water vapor molecules. Forget about the oxygen molecules, the nitrogen molecules, the carbon dioxide molecules. Forget about all those. Just the pressure of the water vapor molecules. That's vapor pressure, and it's really just a way of describing how much water vapor is in the air. Typical vapor pressures range from 0 if the air is completely dry to about 40 millibars or something like that. That would be really humid air. But, it's a smallish number compared to the 1,000 millibars that is the total air pressure. So there will be some water vapor in the air there exerting some pressure. We now have a vapor pressure of more than 0 millibars because we've added some water vapor to the air. So we've added some water vapor to the air, the vapor pressure has increased. Well, what about a little bit later? Well, a few moments later, we still have evaporation. There's still liquid water molecules that are evaporating and joining the vapor, but now there are some vapor molecules up there, each individual one of which has some finite chance of condensing. So some of them are condensing. There's a condensation rate that's not 0 anymore, but really there aren't that many water vapor molecules up there just yet. So the condensation rate is not all that high. At this fairly early stage in our little thought experiment, we will have an evaporation rate that is bigger than the condensation rate, and so since we're adding more water vapor than we're taking away, the amount of water vapor in the air, the vapor pressure of that air in there, is increasing. Great. With time, we can keep adding more and more water vapor to the air in this way until we hit a certain point. At a certain point, there's still water vapor evaporating off the surface of the water at the bottom half of the jar into the air. There's an evaporation rate. But now there's a lot of water vapor molecules up there in that moist air at the top of the jar. There's a lot of molecules. Each individual one has a small, finite chance of being the one that condenses right now, but there's a lot of them up there. It adds up to a fairly large condensation rate. Now we've reached a point where the evaporation rate of liquid water into the vapor is equal to the condensation rate of water vapor back down to the liquid. We're kind of stuck. The change in water vapor now is 0. We're adding just as much as we're taking away. We have now hit a very large amount of water vapor that is in that air parcel, and we can't get any more because it's just condensing out as fast as we're adding it. We could say that this air is holding as much water vapor as it's capable of holding. We would say that this air is now saturated. Saturated doesn't mean like there's nothing in there but water. It doesn't mean anything like that, but it does mean it's holding as much water vapor as it can. So the vapor pressure of the air, when the air is saturated, could be described fairly as the saturation vapor pressure, or the SVP to use the notation on the slide here. So saturation means that the air is holding as much water vapor as the air is capable of holding. Now, there's a caveat here at the given temperature. We'll come back to why that's important later. But the air is holding as much water vapor as it is capable of holding at the present time when the air is saturated. So the saturation vapor pressure is dependent, actually, as it happens, on the temperature of the air. It is telling us how much water vapor the air could be holding. It doesn't mean the air is holding any water vapor. Sorry, it doesn't mean that the air is holding any water vapor. It's telling us how much water vapor the air could be holding at the present temperature. Vapor pressure is telling us how much water vapor the air is holding. So really, this is what we mean when we say that air is saturated. We're not saying that there's no more room for any more water vapor or anything like that, but we are saying that the air is holding all the water vapor it's capable of holding at the current temperature anyway. There's a temperature dependence that we'll get to in a little bit. So the saturation vapor pressure is a measure of how much water vapor the air could be holding. Vapor pressure is the measure of how much water vapor the air is holding, and the ratio of those two numbers is what we mean when we say relative humidity. When the relative humidity is 50%, that means the air's vapor pressure, Vp, is half of the value of the saturation vapor pressure. The air is holding half of the water vapor it could be holding if it were saturated. It's a measure to how close to saturation the air is. So, like air that is saturated has a relative humidity of 100%. Air is subsaturated when it has a relative humidity less than 100%, and air is supersaturated when it has a relative humidity of greater than 100%. Yeah, that can happen a little bit. The vapor pressure can be a tiny bit more than the saturation vapor pressure. But once the vapor pressure is more than the saturation vapor pressure, condensation rate gets really big, and it quickly pulls that extra water vapor out of the air and condenses it out into liquid water drops. Oh, hey, I bet this is what happens in clouds, and you're exactly right. So air can be supersaturated. It can be holding a little more water vapor than it can hold, but only for a matter of moments or something like that, and then the excess water vapor condenses out. So this liquid water is going to be water vapor is going to be condensing out into liquid water drops to produce precipitation. Armed with this idea then of saturation, we can actually come up with 3 different metrics that are going to be used to describe humidity. They're going to be vapor pressure, relative humidity, and the dew point. This vapor pressure idea that we've been using so far in this lecture is actually pretty technical. It tends to be used in like a physical meteorology course. It tends to be used in terms of like equations and things like that, but it isn't really something we can actually measure. There's no piece of equipment that measures vapor pressure. It's more something we use in equations. And we said that relative humidity is just the ratio of the vapor pressure, the amount of water vapor in the air, to the saturation vapor pressure, the amount of water vapor the air is capable of holding. Now that saturation vapor pressure, though, remember, it depends on temperature. The warmer the air is, the more water vapor it is capable of holding, which means relative humidity actually depends on temperature too. This is actually a bummer of a problem. And people really want relative humidity to be a very powerful tool for describing the amount of water vapor in the air, and actually relative humidity is a bit of a disappointment. It does measure the amount of water vapor that's in the air, but it depends also on the temperature, which is hard to sort out, and it's in a complicated nonlinear way. And so it's more accurate to think of relative humidity as being how close the air is to being saturated than to think of it as having like a easy meteorological interpretation, like, you know, it's like somehow it tells you how much water vapor there is or something. The best measure we have for the amount of water vapor in the air is a number called the dew point temperature. It's got units of temperature, like degrees Fahrenheit or degrees Celsius or Kelvin, so it's a temperature. And it is in fact an absolute measure of the amount of water vapor in the air. Now, a dictionary definition of the word dew point temperature would be that it is the temperature to which you need to cool a sample of subsaturated air in order for it to become saturated. At the current temperature, we are holding a certain amount of water vapor. How far would I have to cool it for that to be all the water vapor that air could hold? So, like, here I have a bottle. This is just a close-up picture of like a water bottle out of the refrigerator or something like that, and when you set it on the counter, it started to get this condensation on the outside of the bottle. What happened here? Well, the air around the bottle in the room is not saturated. It has a relative humidity less than 100%, but when that air came into contact with the cold bottle, it started to cool. It started to chill, and cooling it reduces its saturation vapor pressure. So the air is still holding a certain amount of water vapor, but the amount it can hold is decreasing and decreasing and decreasing until eventually we hit a temperature at which the vapor pressure of the air and the saturation vapor pressure are equal to each other. The relative humidity of that air is now 100%. That's the dew point temperature. It's the temperature that we chilled that air to, where now that air parcel has become saturated. Dew point then is a pretty slick way to describe the amount of water vapor in the air, and it's actually an absolute measure. If you know that the dew point now is 60 degrees Fahrenheit and the dew point used to be 55 degrees Fahrenheit, you know there is more water vapor in the air now than there was before. That's not the case for, say, relative humidity. For relative humidity is not an absolute measure of the amount of water vapor in the air. So if we have a relative humidity now of 60% and the relative humidity a little while ago was 55%, we don't actually know that there's more water vapor now than there was before. Could be that the temperature has changed, for example. Dew point isn't like that. It's an absolute measure. It's just the temperature you need to cool the air right now for condensation to begin. It's one of the ways in which we measure we measure the amount of water vapor that's in the air. At an unmanned weather station, it's often the case that they have what's called a chilled mirror. And all it is a little mirror that has, it's hooked up in such a way that it can be cooled, and then there's a laser light source that shines onto that mirror. And it will be seeing its reflection, there'll be like a camera or whatever, it sees the reflection of that laser light off of the mirror. Well, when they chill the mirror down, if they chill it to the dew point temperature, suddenly the mirror fogs over and the sensor doesn't detect the laser anymore, or at least not as much as before. Very accurate way to describe the amount of water vapor in the air. But actually, there are plenty of other instruments that we can use to measure the amount of water vapor that's in the air. Official weather observations at a manned weather station are taken with a piece of equipment called a sling psychrometer. It's two little thermometers on a handle, as you can kind of see in this image here. And one of the two thermometers is wrapped up at the end with like a piece of cotton, and that cotton is wet. Well, like for example, when you step out of the shower, when you're wet and you touch the air, you get cooler due to the evaporation of water off your surface. In the same sort of way, we can get a measure called the wet bulb temperature that comes from this wet thermometer. You compare the wet bulb temperature to the dry bulb temperature, and it takes a fair amount of math, but it can be converted from that into dew point or relative humidity or vapor pressure or any other measure of water vapor that you need. Less accurate measurements of water vapor can be taken with little pieces of electronics, like this is actually a hygrostor, I believe. These can be very small and very light, easily carried by things like weather balloons and so on, or in cheap household electronic devices. Like I have a little weather station here in my office right here, and it's telling me right now the relative humidity in this room is 39%. I'm sure there's some cheap little hygrostor in here that is measuring the humidity. It's probably not particularly accurate, but it's light, it's cheap, etc. We can put it on something like a weather balloon and it can just float away. So we can do that though. We can get the humidity at different levels in the atmosphere by putting these instruments on board a weather balloon and having it fly away and get the measurements at different heights in the atmosphere before the balloon pops and falls back to the ground. Alright, armed with this information about humidity, we're going to talk about one last topic in this unit, in this module, to use the right term from online teaching, and that is clouds. So continue on to the clouds lecture, and let me know if you have any questions.